Hi all, welcome back to Kinetic Theory of Gases Part 2. In the kinetic theory of gases, we seek to explain the behavior of gases by considering their motion of molecules. The macroscopic behavior of an ideal gas can be described by using the equation of state, but the microscopic behavior only can be described by kinetic theory of gases. This is the assumption that has been made in kinetic theory of gases. All gases are made up of identical atoms or molecules. All atoms or molecules move randomly and haphazardly, or we call it freely. The volume of the atoms or molecules is negligible when compared with the volume occupied by the gas. The intermolecular forces are negligible except during collisions. Interatomic or molecular collisions are elastic. The duration of a collision is negligible compared with the time spent traveling between collisions. Atoms and molecules move with constant speed between collisions. Gravity has no effect on molecular motion. So for the PSPM spec, you all have to know only 4 or 3 of the kinetic theory of gases. You can choose the first one. All gases are made up of identical atoms or molecules. You can choose the second one. All atoms or molecules move randomly and haphazardly or freely. You can replace haphazardly to freely if you want to do so. No problem. Or you can choose this one. Interatomic or molecular collisions are elastic, or we call it the collisions between molecules are completely elastic. It is because when molecules collide, there is no exchange of energy. Or we make it this one. The intermolecular forces are negligible except during collisions. Intermolecular forces is force of attraction. So force of attraction between molecules is negligible. So you can choose any of these if the questions asked you to state the assumption of kinetic theory of gases. How to measure the pressure of a gas in a cubic container? And we're going to derive one solid formula for pressure of a gas. But don't worry, for your PSPM syllabus again, you all don't need to know how to derive the pressure of a gas, but you have to just use it. So don't worry much, or just munch something while watching how to derive the pressure of a gas. Figure shows an ideal gas in a cubic container of length L. The velocity of a gas molecule of a mass m is v. The components of the velocity v along the x, y, and z directions are t, u, and w respectively. So the velocity of a gas molecule of a mass m is v square equals to t square plus u square plus w square. Let us consider the component of velocity u towards the wall x. Since the collision of the molecule with the wall is perfectly elastic, the velocity after collision is negative u. So the change of momentum is negative 2 mu. By assuming there is no collision between molecules, the time interval between the collision of the molecule with the wall x and the next collision with the same wall is about t equals to 2L over u. Hence, the rate of change of momentum due to one molecule is F, which is equals to mu square per L. Now, the total force exerted on wall X by all the gas molecules F, which is equals to N times mu square over L. You're going to get n times mu square over L, where n is number of molecules. Now with a large number of molecules of varying speed in random motion, the mean square of the component speed in any one of the three axes is the same. So the mean square speed of the u equals to mean square speed of w equals to mean square speed of t. This is the symbol of mean square speed, is 2. By adding all together, the mean square speed of u equals to 1 over 3 of mean square speed of v. By using the Newton's law too, F equals to ma, where F equals to m times mean square speed of u divided by L. By substitute mean square speed of u equals to 1 over 3 of mean square speed of v, you're going to get the total force exerted on the wall. You're going to do the same process to find the total pressure exerted on the wall. So the pressure is equals to F per unit area. Area is L square and F is m times mean square speed of v over 3L, and the pressure is m times mean square speed of v divided by 3L cube. L cube here is volume, so mass per volume is density. So total pressure exerted on the wall is P equals to 1 over 3 times density times mean square speed of v. By giving the assumptions of average speed of all molecules is constant, everyone knows that the pressure equals to 1 over 3 times density times mean square speed of v. Therefore, the root mean square speed of a molecule is equals to square root of 3 times pressure over density. So this is the symbol of root mean square speed, VRMS, which is square root of 3 times pressure over density. As I mentioned earlier, for your syllabus or scope of PSPM, you just have to use this formula. You can use for root mean square speed or velocity as well. Simple like a bubble without giving you any trouble. And you don't need to know how to derive this. To make yourself confident, let us attempt one A-level questions. Estimate the root mean square speed of air molecules at 27 degrees Celsius and 1 atmospheric pressure or 101 kilopascal if the density of air under these conditions is 1.29 kilogram per meter cube. By apply or use the formula of P, pressure equals to 1 over 3 times density times mean square speed of V, and substitute all the values accordingly into this formula, you will get the root mean square speed is about 485 meter per second. By attempting the A-level questions just now, hope you all understand how to use the root mean square speed, which is equals to square root of 3 times pressure over density. We have two options to find the root mean square of molecules. By relating this formula with an ideal gas equation, we're going to get VRMS equals to square root of 3 times molar gas constant times the absolute temperature divided by molar mass. And we have another option by relating an ideal gas equation with Boltzmann constant K, and you're going to get VRMS is equals to square root of 3 times the Boltzmann constant K times the absolute temperature divided by mass of a molecule gas. So you can find the root mean square of the molecules by using these three formulas. Thank you for watching this video. Thanks a lot, and thank you to the Lord.